So, last week we started to see routing protocols. Okay, when you have directly connected networks, you don't need a routing protocol because the router knows how to forward to the networks because they are directly connected to it. But networks are not always directly connected, so I need to know how to reach distant networks or networks that are not directly connected to me. I can configure static routes. We saw that this might be enough. For example, at our homes, when we only have a link outside, we can have a default route, a static default route. And it's good enough because I don't have any more networks that I need to know besides the default one, which is every network, because all networks are accessible via that link. But in more complex topologies, I need to know if I need to go right or left, or I need to know if I need to go to one neighbor or the other to reach different networks. Okay, so we saw that in that case I need to learn the routing information of other network elements, and for that I use a routing protocol. There are three actually big sets of routing protocols: distance vector protocols, link state protocols, and then there's BGP, which is a path vector, which means it's similar to a distance vector in terms of in theoretical terms, but instead of distances, it announces paths. That's a big difference. So today we're going to start with the distance vector protocols, and we're going to see an example, which is EIGRP, which is a protocol from Cisco, which is basically the most complex distance vector protocol that exists. There's another one called RIP, which is in its sixth version, I think, but it's not commonly used. Actually, even EIGRP it's used in small networks, like small enterprise networks, but it's not that much used also. Most of the time people use OSPF or ISIS, which are link state protocols, because they have certain advantages. Why? Because distance vectors work how? They advertise routes as vectors. Okay, so the distance part of the name is because they announce a distance. Okay, a distance to a given network. That distance is the cost of a route, and how do I identify the route? Through a vector. What is a vector? The vector is the interface that I need to use to reach the network. Okay? So what happens in the distance vector protocol is that each router starts in the beginning. It only knows how to reach its own networks, its own directly connected networks. So it's going to start by sending a zero distance, okay, a zero distance to its directly connected networks. For example, a router starts, it only knows its networks that it has. Imagine that it has 3 networks. The first distance vector that it's going to send to its neighbors, he might have neighbors here, okay? He might have 3 networks. For example, imagine that there are 3 VLANs here, that this is a layer 2 topology with a VLAN, this is another layer 2 VLAN, this is another layer 2 VLAN. So each one is its subnet. So in the beginning, the router is going to send, and here he has a neighbor. So in the beginning, what he's going to say is that he can reach these 3 networks with 0 cost, okay? And this arrives here. So what this router receives is a distance, which is 0. It receives three different distance vectors, all with 0 cost, and all with the same vector in this case, which is this link here. Okay? And then this is going to start to build up. So this router is going to do the same thing with its neighbors, and this router might have its own networks. So in the beginning, he will also send an update here with 0 cost for this network, 0 cost for this network. So this starts by learning networks at one hop. Okay. So in the beginning of a distance vector protocol, a network that is operating a distance vector, they all start to learn routes only at one hop, okay, which is each one tells to its neighbor the directly connected routes with the 0 cost. And then when the distance vector starts propagating, at each step the routes grow in terms of the number of hops, okay? So as you see, the routers do not learn the entire topology. They only learn the distances for the networks that the neighbors announce. Actually, this process that I was describing is an implementation of a known algorithm which is called the Bellman-Ford algorithm. It's a distributed implementation of the Bellman-Ford algorithm. And it's distributed because of this, because each one in each step is adding another hop of network exploration. So everybody starts by sending their own directly connected networks, and then when they learn the directly connected neighbors the directly connected networks of their neighbors, they propagate that to the next neighbor, and then the paths are increasingly growing in number of hops until they span the entire network. Okay, so EIGRP is a distance vector protocol with some characteristics that are not usual in distance vectors. Namely, these ones here. It allows load balancing across equal, which is normal in all distance vectors, but also in unequal cost paths. Okay, we will see later. So usually distance vectors only allow the simultaneous use of 2 different paths for the same network if they have the same cost, exactly the same cost. But in EIGRP, it's possible to have unequal cost load balancing. Also, the metric is more sophisticated than, for example, in RIP. Okay, it can use a mix of parameters to calculate the cost of a link, while in other distance vector protocols, it's usually just the hop count or just the bandwidth. Okay, and also another different thing: usual distance vector protocols exchange periodically distance vectors. In this case, it only exchanges distance vectors when something changes in the topology or when the neighbor asks for an update. Okay, so why aren't distance vector more used? They are simple. If you paid attention, you saw that nobody has to do a lot of calculations in a distance vector. The router simply receives a distance from the neighbor and adds its own distance to that neighbor. So I receive a network, for example, that 10.0.1.0 is reachable via this neighbor with some cost, 50. The only thing that this router has to do is add the cost of this link to this value. Imagine that this link costs 10. The only thing that I have to do is add 10, and now I know that I can reach this network with a 60 cost. And then the only thing I need to do is send this update to my other neighbors with the 60 cost. And everybody just adds their local cost to the cost that they receive, and there isn't a big calculation here. There's some drawbacks to this, and that's why most of the time, whenever possible, people use link state protocols. Link state protocols are more complex because each router knows the entire topology, and each router needs to perform an algorithm to find the shortest path tree from itself to every other node. So it has to calculate a spanning tree with himself as the node. So it has to compute an algorithm, usually it's the Dijkstra algorithm, locally. And in case of the distance vectors, nobody has to calculate an algorithm locally. They are all calculating an algorithm, but in a distributed way. What's the distance? So distance vector protocols are less complex. They scale better, okay? Because no router needs to know the entire topology, and the only calculation that they need to do is a sum, and then a minimization of that sum. So they only need to sum their own cost to the cost they receive. Then they have to choose the smaller cost and announce that smaller cost to the neighbors. But this has some problems. Distance vector protocols suffer from different problems. For example, the count to infinity problem, which might happen when you have failures. Why? Imagine that you have so this router here has 3 different paths to a given network here. Actually, we might put another router here just for more complexity. So what happens here is that this is a network here, okay? I have a network here. So this one is going to announce here, is going to receive from here, is going to receive from here, is going to receive from here. But he's only going to choose one. If he has more neighbors to this side, he will only send the smallest cost one, okay? Imagine that the smallest cost one is this one here, okay? He's only going to announce this path here, okay? And everything is working fine. So these routers here, okay, they know the path from here. Now, all of a sudden, if this link fails, so this link no longer exists, what's going to happen is that I need to use one of these 2 alternative paths. But in a distance vector, this can take some time. Because when this router loses this link, it's going to announce here that his cost is no longer the previous cost, but it's now this cost here. Okay? Oh, this was a bad example, not this link failing. This link failing. If this link fails here, okay? Because this link is shared through all routes, okay? So if this link fails here, what happens is this router will tell this one that he no longer has, imagine that the cost here was 10, and from here is 40, and from here is 60. So what he's going to say is that he no longer reaches X with a 10 cost because this link failed. He now reaches X with a 40 cost because he goes to this. Immediately he's going to announce this path. But if you see, this path will no longer exist because this link also affects this path, okay? So he's going to send this update with this, and then a while he's going to see that. Why? Because at this point he does not know that this path is no longer available, because here I only have a link. So this router lost this link, and immediately he told this one that this link does not exist. So this path disappears. But the update is still propagating through here. So at this point, he knows that this path disappeared, but he does not know that this path also disappeared, because this path has 2 hops, so the update is going to take longer. So he's told back that he has this alternative because he hasn't learned yet that this alternative has also disappeared. Okay? And this is why this is called count to infinity, because I can be successively giving paths that are all affected by the same link up until the point where all the updates have propagated, and now I know, okay? So this is a lot slower, this process, and sometimes it might not even converge. This is a lot slower than in a link state, because in a link state the process is different. In a link state, When this link fails, what's propagated is that this link failed. Not that there were cost changes, not anything like that. What's propagated is that this link changed, and everybody gets this update, and then everybody recalculates Dijkstra without this link. So everybody is going to learn at the same time that this link doesn't exist. Because in this case, I'm not propagating distances, I'm propagating link states, I'm propagating how the links are. And nobody changes anything until they know that the link disappears. And when the link disappears, they all know that all the paths are invalidated. All paths that go to that link cannot be used. In a distance vector, I don't know that. During some time, I don't know. I might be changing to another path with a bigger cost that in a few milliseconds will also disappear because it's affected by the same link failure. Okay, so distance vectors are better, they scale better because the routers can have less processing power, they don't need to calculate Dijkstra, they only do additions and then minimization, meaning choosing the lowest cost. They converge, they take more time to converge, and they have these problems of consecutively exploring longer routes until they finally know that those longer routes are also affected by a failure. Okay? Nonetheless, if I have big topologies, or if I have routers that are not very capable, I might need to use a distance vector protocol. And this is the reason why BGP, that we will see after the first test, is not a link state protocol. The routing protocol of the internet, which is BGP, is not a link state protocol. Why? Because no router would be able to learn the entire topology of the internet. Okay? And a link state router does that. It learns the entire topology. It has to know the entire graph. Actually, in link state protocols, even in small networks, we have to divide the network in several different areas, because it's very computationally heavy. But it has the advantage that it's much quicker to converge after failures, and also usually link state routers take better decisions because they know the entire topology. So in this case, EIGRP runs on top of the IP layer. This means that it's an IP packet, and then there's a protocol for EIGRP, which is 88, you see. It's in the same header. The packet might be TCP, UDP, or EIGRP. There's other protocols, of course. But EIGRP is a layer 4 protocol, okay? So it sits on top of IP, okay? But this is a control protocol that runs on routers, and they need to exchange information, and they use this layer 4 protocol to exchange that information. So, being a layer 4 protocol running on top of IP, EIGRP is connection oriented, so it works more like TCP than like UDP, because it assures reliable ordered packet delivery. So it has sequence numbers and all those things to recuperate from failures and assure ordered packet delivery of all packets. There are five types of messages: hello, update, query, reply, and acknowledge. The hello message is the first one that is exchanged when the neighboring is first established. After the hello packet, the router sends the first update, and the update contains what? Distances to networks that are reachable via that router. Which ones? The smallest ones. Okay? If the router learns 2 ways to reach the same destination, it only announces in the updates the smallest cost one. Okay? So it's like it's in this picture. hello between R1 and R2, establishing the neighboring. The neighbor receives the hello message, sends the first update with the complete routing information, so its own distance vectors, and then an acknowledge is sent. Okay. After the acknowledge, the router sends its own update. An acknowledge is sent, and the neighboring is done. After this initial neighboring process, they only exchange updates when something changes. Okay? So routers 1 and 2 will only send update messages if they received an update from another neighbor that gives a better cost for a given network, and then he updates that and sends the update to the other neighbors, or if a link failed and the cost went higher. Okay, so only when there are cost changes to reach a given network, only in those cases an update is sent. Besides the normal updates, a router can query a neighbor to receive the distance vector at any given time. Okay, this might happen because the router lost something, or he wants to know the distance vectors of a neighbor again. He can send a query, okay, and he will receive a reply, and he must acknowledge that reply. The contents of the reply to a query are the same that the same as in the update message. So after this process is done, I have neighbors. After configuring EIGRP, we will see how we can do that later. You can do show IP EIGRP neighbor, and it will show the neighbors with him he has formed an adjacency. Okay. Usually the term that is used is agency. Okay, between two neighbors. In this case, he has three neighbors. One via the serial interface 000.4, another one via the serial interface 000.1, and another one via the fast Ethernet 00 interface. So it has three neighbors. You can see here the time, how many minutes this neighbor relationship is up, this agency is up. Then you can see, if you have neighbors, you are learning routes from that neighbors. Okay, a route in a distance vector is a network and the cost to reach that network. So if you go and show and do the command we saw last week, show IP route, besides the directly connected routes, you will now see routes that are learned via EIGRP. Okay, they have a special code, which is this P from passive or active. In this case, because the command was show IP route EIGRP, so it only chose the ones that were learned from an EIGRP neighbor. Actually, this is not the routing table, this is the topology table. Okay, it's show IP. I can't see here because it's very small, but it's show IP EIGRP topology. Okay. So this tells me everything that every neighbor has told me. So in the topology table, I can have more than one route to the same destination. Okay, so in this table, I can have 2, 3, 4 routes for the same destination. Actually, in this case, we only have one for each. We have one for 192.168.1, one for 192.168.2, another one for .3, and another one for 10.1.115. So all different networks. But in the topology table, I might have for the same network more than one route. Why? Because I can learn routes for the same network through different neighbors. Okay? And in the topology table, I'm going to store the routes for the networks from all neighbors. Then I'm going to choose the better one, the one with the least cost, and that's the one that I'm going to install in the routing table. So in the routing table I only have one route for each network. There's never two different routes for the same network on a routing table. Okay. So for example here, we are looking to the neighbor table of router 3, this one here. It has two neighbors, neighbor R1 and neighbor R2. Okay. Neighbor R1 through the Ethernet 0 and neighbor R2 through the Ethernet 1 interface. Then, in this case, he receives, for this network here, he receives two different distances, okay? He receives one via the R1 router and receives another one via the R2 router, okay? So, I have, in the topology table, I have both routes for the same network, okay? But they have different distances. In EIGRP, the distances are called the advertised distance, or AD, and the feasible distance, FD. Okay? The advertised distance, as the name says, it's the distance that my neighbor advertises to me. The feasible distance is the sum of the advertised distance plus the local cost. Okay? For example, here, R1 is going to announce with an advertised distance of 500 plus 500, 1000. And the feasible distance will be 1000 plus the cost of this link, which is the same as this one. It's 1000 also. So the feasible distance will be 2000. Okay? Here it is, 2000. From R2 is going to receive an advertised distance of 500 plus 500 plus 500, so it's going to give an advertised distance of 1500. Then, okay, if ID is 1500, I'm going to sum the local cost, which is 1000, the cost of this link here, and I get 2,500 cost, okay? So both are in the topology table, but in the IP routing table only the best one is installed. And if he has a neighbor here, okay, imagine that I have an R6 here, a neighbor R6 here, I only announce this route, okay? So R6 will not know that this exists, okay? So R1 knows that this route exists, but this router here does not know, okay? Because each one only announces the best cost. So this is another disadvantage compared to link state, because R6 does not have full knowledge of the topology, okay? So routers in link states usually make better decisions, okay? So topology table, all routes that I learn from all neighbors, but then I only propagate the best one. Okay, so we already saw this. Advertised distance is the cost between the next hop to the destination. Feasible distance is the advertised distance plus my local router cost, so plus the cost of the link to the neighbor. The route that is selected to go to the routing table is the one with the lowest feasible distance, and also that's the one that's announced to other neighbors, okay? And that route is called in EIGRP the current successor, okay? So the current successor is the next hop router with the lowest feasible distance cost. But then I can have a different successor called the feasible successor, one or more, okay? And the feasible successor is a backup router that has a loop-free path to the destination. What's a loop-free path? So, it's if I have a neighbor that announced to me, in this case here, I have this destination, okay? And I receive this from this router and this router, okay? So the best path we already saw is VR1, which has 2000 cost. So this is the feasible distance. So if my distance to the destination is 2000 and R2 is giving me a route, with an advertised distance of 1500, okay? This means what? This means that R2 is closer to the destination than me, right? Because if my shortest distance is 2000 and his shortest distance is 1500, he's closer than me. And this means another thing. This means that the route that R2 has to the destination does not pass through me. Because if it passed through me, the cost would have to be higher than 2000. Okay? If I'm going from Lisbon to Porto, okay, and it's 300 kilometers, and then Coimbra tells me that for reaching Coimbra, to go to Coimbra to Porto, it's 200 kilometers. So I know that if I go to Porto through Coimbra, I will not come back to Lisbon again, because otherwise the distance will not be 200. It will have to be higher than 300 kilometers. Okay? But if I go through Setúbal, and he tells me that the distance his distance is 350, then I don't know if I go through Lisbon or not. I might not. I might use another path that doesn't go through Lisbon, and it would be okay. I would not have a problem, no loops. But only with the information of the distance, I'm not sure. Because if he tells me that his distance is 350 and mine is 300, I can't be sure that the path that he's telling me that it is 350 kilometers is not a path through me. And if it is a path through me, we have a problem, because I will send packets to Porto, to Setúbal, and then Setúbal sends it back to me, because the 350 kilometer path is through Lisbon. And then Lisbon receives the packet and sends again to Setúbal, because it shows the path to Setúbal, and the packet never leaves, and it's in what we call a forwarding loop. Okay? So, but if the advertised distance is smaller than the feasible distance, I know that I won't have a forwarding loop. I know that if I send a packet here, he will never go back here, because otherwise its distance would have to be higher than 2000. Okay? This would mean that I had a path like from here and not here. This one would not exist. And then he has a path that goes through here, which is 500 plus 500 plus 1000 plus this link, 2000. Okay, so he will tell that he has a 2500 path. But this 2500 path is going through R2. Okay, it's this path like this. Okay, actually in this case this wouldn't happen because actually this doesn't stop here, right? So R3 is going to send an update here telling that it can reach this destination with 2000, okay, with 2000 cost. And R2 is going to learn here that it has a route which is 2000 plus 1000, 3000, okay, via R3, okay. But this route is never sent back here, because it does not make sense to announce a route to a neighbor if that neighbor is the next hop of the route, because I immediately know that that's a forwarding loop, okay? But this could be trickier. I have an example here later, okay? Actually, I can go here just in. this is, I'm going to show you this slide because we are talking about this. But for instance, in this case here, we have the same situation. This is the network. So I'm going to announce to R8, yeah, and then R8 announces to R1, and then R1 is going to announce to R2, okay, and it's going to announce to R4. But R4, this route here that it's announced here, R4 does not announce it back. Why? Because this route is via R1, so he immediately knows that it can't be used. Okay, I can't say if I go back to the example of Lisbon and Setúbal, if Setúbal tells me that his best route is through me, I'm not even going to accept that. Okay, because I know that I'm going to send to him and he's going to send to me. But this one is not a problem, but this one here is. Okay, you see, R8 receives with 20, he actually receives with 10, which is the cost here, adds 20. So R8 receives with 10, it adds 20, it gets 30, and then sends to R1. R1 receives 30 and adds 100, so it gets 130 via R8. Then R1 sends to R2 with 130, so R2 gets a route with 230 via R1, and then R2 sends this to R4, and R4 gets a 330 via R2 route, all to the same network. Okay, and now R4 is going to send this to R1, and so R1 is going to receive one with 430 via R4. You see, this is going to happen in the distance vector. This is going to be in the topology table of R1. Okay. All of them. I'm said this is sending, this was sent with this, then this went to R8, R8 added the 20 and got 30. This one sent to R1 with 130. Okay. And then this one sent to this one, and then this one sent to this one.
For example, we try to send the package, right, through R1. And what I want to know, what's the final destination, like through this?
The final destination is this. This is all to this network. If you want, we can do the routing tables of them all. Maybe it's easier. So R7 has only to this network. R7 has directly connected with cost 10. Okay, directly connected. Then R8 receives only one route. Okay. Via R7 cost 20. Okay, R1, I'm going to leave some space for R1 because he's going to have more. For now, R1, yes, it's 30. You're right, it's 30 because it's 20 plus 10, it's 30. So R1 is going to have 130 via R8. Okay. Now R2 gets this update, adds this 100, and so he knows how to reach that network via R1, because he received it via R1, with cost 130 plus 100, 230. And now the update reaches R4. R2 sends an update to R4, so R4 has a route via R2 with 330. Okay? R4. Now R4 only knows this route, okay? So it's going to send this route to its neighbors. So another route will appear on R1, okay? Another route appears here, sent by R4, with cost 330 plus 100, 330. Okay? And then R1 received another route but it won't propagate more. Why? Because it only propagates the smallest one, and he already had one with 130, so he won't send this to anyone else. Okay? But he gets both routes. Okay? So same thing, R1 will not give back to R2, and then this stabilizes with this state. Okay? The only one that has two routes is R1. Okay? So what's the problem here? No problem. This is the normal behavior. And this is only in the topology table. In the routing table, I only have this one. And this is the one that I only announced this one. I already did. So when I receive this, nothing changes. I don't give this to anyone else. So I'm stable. The problem now is if this link fails. Okay? If this link fails, and we talked that EIGRP allowed the use of feasible successors, which are backup routes that can be readily used when something fails. So imagine that this route was used as a feasible successor. What would happen is that when this fails, I immediately start using this route. Okay? But this route has a problem because this route is via R4, and R4 will send via R2, and R2 will send via R1. Okay? So the packet does this and reaches here again. And again, if I'm using this route, again I'm going to send to R4, and the packet is trapped here. Okay? Why is this happening? Because I'm using this as a current successor, and I can't. Why? Because the advertised distance of this route, which is not here, so this is the feasible distance, but the advertised distance was 230. Okay? Then he sums the 100 of its link and gives 330. Okay? And this is the advertised distance of this route is higher than the feasible distance, the current feasible distance, which is 130. So in this case, I cannot use this route as a feasible successor. Okay? Now, could this happen if this feasible distance was smaller than 130? If this was smaller than 230, for example 50, then this could be used. Why? Because it's impossible, you see, if this is in order for this to be smaller than 130, the path cannot go through here. Because if this path via R4 goes through myself, then this means that it has to be higher than 130, because my best path is 130. So it has to add something. Okay? This is why I know if this is higher, I'm going to have a problem, or I might have a problem. And if it's lower, I won't have a problem. Because if this is lower, this would mean that R4 had a direct link here. This is the only way in which this can be lower. If I had a direct link here with, for example, 20, okay? Then this would give 30. Actually, this would be, 20 is a bad example because this would be the feasible successor, because it would be the, but if it has, this is 130, so it's difficult here because this link is 100, this cannot be higher than 20, because it's going to sum 100 and then it's going to give 120, and it's going to be lower. Okay? No, but I can have here, yes, this does not count in this case. I can have here up to 130, for example 120, and in this case I will have a route which is 220, so higher than that one, 120 plus 100. Okay, but in this case I have 3. Okay, if I have this link now in R1, I will have 3. I will also have this one with 330. So I have this one with 330, which is this one like this. Okay, which has a loop. So this one is not a good one. This one is the one with 330, but I also have this one. So in the topology table, I have 3 now instead of 2. And this one we already saw it cannot be used, but this one can, because this is 220, but the advertised distance is only to 120, which is smaller than 130, which is my feasible distance. So in this case, this can be used as a backup route, because now this can happen, okay? It was impossible to have a path going through me that is lower than 130, okay? But if it's not going through me, it can be lower. For example, this could be 300, and I have a possible path with no problems. But since I do not know the topology, the only thing that I know are the costs, I still can't use them because I don't know, okay? I don't know if this goes through here or if this goes through me. Because since this is bigger, I have no guarantee. Okay? It might be or not.
What happens when there's two routes with the same distance, the same cost?
That's not a problem. They can both be used at the same time. In that case, they can be used at the same time, not even with failures, because feasible successors are usually only used in failure cases, but the ones that have the same cost can be used simultaneously. Actually, you can do a configuration, we will see in the final part, where you can even use feasible successors to load balance also. Okay? But then you have to configure a command which is called the max spots, which usually by default is 4, but if it is 1, or the feasible successor cannot be used only in case of failure. If that is configured for more than 1, then the feasible successor can be used even for load balancing. Okay. The same cost ones can always be used in for load balancing, even if the max paths command is 1. Okay, so we will skip this when we get back here, but this was just to understand this rule of the advertised distance being less than the feasible distance. And if this rule is true, I can use that route, okay? I can use for load balancing, or I can immediately also use in case of failure. Okay, so the topology table is changed when the cost changes or if a link fails, okay? Or if an entire router disappears, which for the neighbor is the same thing, because if the link fails, he does not know if the neighbor exists or not. Okay? When something like this happens, when my topology table changes, I have to choose another route to update to the other neighbors. Okay, so I have to see what is the least cost route now and propagate that one to my neighbors. See that although we can use non-equal cost paths in EIGRP, most of them are not known because I only know that I have 2 paths. Remember in the example that we were saying, only R1 knew of 2 different paths. The other ones did not knew. Why didn't they knew? Because R1 only announces the best one. Okay, so nobody else gets to know that there are 2 alternatives there. Okay, if we had that case here, only R1 here. For example, this one will know from here, but not that on R1 there's 2 possibilities. Okay, so this is what we have been doing. The algorithm is another example. Okay, in this case we have here 10, so we will have here what? A route with 130, another one with 20, 21, 121, and another one with 20, 40, 140, 240. Okay, that's what we have here. One with 30, another one with 21, another one with 140. Via the 3 different neighbors. So in the topology table, I have all of this in this router on the left. Okay? And the feasible distance is summing the 100. Okay. So I have in the topology table 3 possibilities. I'm going to choose the one with the smallest feasible distance. Okay. So this is the chosen route, the successor. Is there any possible feasible successor? There is, because this route here has an advertised distance of 30, okay, and 30 is smaller than 121, which is the feasible distance of the successor, okay, and this is the advertised distance of the possible feasible successor. And since this is true, this one can be a feasible successor, meaning what? Depending on that command, the maximum path command, R1 can use both at the same time for load balancing, or at least when there's a failure on the successor, he can immediately start using the feasible successor. Okay. The other one, which are these both, this is the best one, and then this is the one that can be used as a feasible successor. The bottom one cannot. Okay, although in this case there's no problem. Okay, in this case there's no problem, there's no loop. The path from R4 to the network does not pass through R1 again. But since the advertised distance that he's giving me is 140, I cannot be sure. Okay, it might be a path like this, for example, which would be the same, 121 up to here, and then plus 19. So R1 does not know. It can be something like this. Okay. So this one cannot be used, although in this case there's no problem. So this we already saw is the case in where it can be a problem. The cost in most distance vector protocols is basically the bandwidth. So each link has the cost associated with the bandwidth. So usually the better paths are the paths with the least amount of hops. Except when a path, for example, has 3 or 4 links but with very high bandwidth, and then there's another one with 1 or 2 but with very low bandwidth. But usually links all have kind of like 2 or 3 bandwidth types. Okay, if they are gigabit Ethernet, they have 1 gigabit. If they are fast Ethernet, they have 100 megabit. Okay, so usually, most of the time, the smallest hop count is the one with the smallest cost. EIGRP, besides the bandwidth, also uses the delay, which is being measured, the reliability. So it goes and sees in the logs how many times that interface, for example, was shut down or was broken. Okay, if it is an unreliable link, it will have a higher cost, and also it tries to use the load, the average load of the link. So if a link is more loaded, it will have a higher cost. Usually, if you want to change the cost of a link, you can use any of this. You can change manually using a command the value of one of these parameters. The bandwidth is the most important one. Okay. So we saw all these more theoretical things on how these protocols work. How do we configure this? An important part is, if I'm going to have a layer 3 network, I have to be careful on how, if I'm talking about an enterprise network, because if I'm talking about the internet, then the prefixes, I already have the prefixes. They are given by IANA, which is the internet registry. So I have that networks and I have to work with them. But if I'm in a private network, if I'm in a service provider in the interior gateway network, or in an enterprise or campus network, I should plan how I'm going to use the IP addresses. Okay. So in this figure here, what you have is each one of these stubs here, you might think of them like a VLAN, okay? So actually this here is simulating an entire layer 2 network. It can have multiple switches with trunks, okay? Whatever. What this means is that on this interface here, I have this subnetwork, and this subnetwork can have a lot of hosts that are connected in a switch or whatever, okay? Or several switches exist here with a spanning tree. So this is a VLAN, a subnet, okay? So I have all these ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? And then, for example, in this case, this topology has a core, okay? So these are access routers, so the VLANs are connected to them, and then there is an aggregation router in each one, which is these ones here. And then there are these 3 cores in a ring, okay? 3 core routers in a ring. So I have all these VLANs, each one with its network, and I have to decide the networks that I'm going to give. And if you see here, all the networks that are accessible via this router, which are these ones here, I was careful to place them in contiguous subnets. You see, it's from 10.3.1.0 up to 10.3.4.0/24, okay? So networks .1, .2, .3 and .4, okay? Why? Because I can now announce here only 10.3. In this case 10.3 because in here I use 10.2 and here they use 10.1. Okay, so here I can simply use 10.3.0.0/16. In this one here I'm going to announce 10.2.0.0/16. And on this one, in this one here, we'll only announce 10.1.2. This is .2.2, sorry. This is 10.2.2.0. And this is exactly, so I can do 10.2.0/16. This one can be 10.3.0 and this one can be 10.1.0/16. Okay, you see, so this router here only knows these 3 networks instead of 12, okay? Instead of knowing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So instead of 11 entries in the routing table, I only have 3. Okay, so the longest prefix match will be much faster. Okay, and why? Because it does not make a difference. Okay, because these 4 networks, there's only one path, which is via these routers. Okay, so I can announce a bigger prefix that includes them all. Okay, the rule is the prefix can be, it has to be big enough to include all of the networks here and not too big, okay? It can't include any of these ones, okay? For example, if instead of 10.2 there we used 10, we could use, for example, 10.3.1, 10.3.2, and 10.3.3 here, and in this one I could use 10.3.4, 10.3.5 and 10.3, the 1, 2, 3 also, .6, okay? And then in these ones here I could have used 10.3, not 7, and we will see why, but 10.3.8, 10.3.9, 10, 10.3.10, and there are 4 networks here, and 10.3.11. Okay, so this is also a possibility, and I can still do a summarization, but I can't do a summarization as I did before. For example, here I cannot say that I have 10.3.0.0/16. Why? Because this also includes these networks and also includes these networks, which are here, now, and here. So I can't say here that I can reach this and I can reach this. I'm going to have a problem, because then this router is going to be confused, because he's going to receive this from here and this from here. Okay? But I can still summarize. Okay, I can use a 10.3. I can use a 10.3, for example, .0 slash. I need this to change from 4 to 4 in groups of 4. Okay, so that in the first one I include from 0 to 4, which includes these ones. On the other one I include from 4. The 4 actually is from 0 to 3, because 4 is the next network. So in here it's from 4 to 8. That's why I could not use 7 here. And now this one is from 8 to 12. Okay, this is if I use a mask where networks change here in groups of 4. And this is if I want to change in groups of 4 here is a /22. Okay. /24, it changes 1 by 1. /23, it changes 2 by 2. /22, it changes 4 by 4. So this could also be a possibility if I had these networks instead of these ones here that are more simple to do. Okay, so the main thing is when you are doing routing, we should choose contiguous networks. Okay. So networks that I can group together in a slightly bigger subnet, okay? Because this facilitates summarization. If, for instance, here I use here I use the 10.3.1, 10.3.2, but then use the 10.3.16, I no longer have a good subnet to summarize this. In this case, I would be forced to use the 10.3.0.16, which is already a very big subnetwork. I might not have that much addresses. Okay. So you have to think about these things. Give the networks, look at the topology, see where the possible summarization points are. Okay, and then we're going to start to configure this. What we need to do, EIGRP is an interior gateway protocol. So it's a protocol for routing inside of an autonomous system. Okay, an autonomous system is a network that is managed by a single authority. Okay, for example, the internet is not an autonomous system, because in the internet I have several autonomous systems connected between them. And we have routing in the internet, but in that case, internet is an exterior gateway protocol. It's a routing protocol between autonomous systems. And this is an interior gateway protocol, so routing inside of an autonomous system. So I will have to choose an IS number, choose the IP addresses, and then I have to say which networks will be included in EIGRP. Okay? Actually, it's the networks and the interfaces. Okay, I have to say to a router, this interface will belong to EIGRP, and this means two things. It means that I'm going to try to make a neighbor relationship to the other router that is connected via the interface, and I'm going to announce a distance vector of 0 to the network of saying that I can reach the network of that interface. So it serves two purposes. when I configure an interface to use EIGRP, I'm doing two things. I'm configuring the interface to form a neighboring relationship, and I'm telling the router to announce the network of that interface. Okay. This is important because it's something that you usually mix up. Okay, so we're going to see configuration. For example, here, R1 wants to form a neighboring relationship with R2 and wants to announce via EIGRP this network and this network, but not this one. Okay? This is an external network and I do not want it to be part of EIGRP. This means what? I do not want R1 to tell this neighbor that it has this network directly connected, okay, with cost 0, nor that it has whatever networks he learns from R3 with whatever cost, okay? So how do I do this? So first, the configuration is we go to configure terminal, configuration mode, and then we enter the routing configuration mode with this command, router. In this case, router EIGRP, which is the protocol, and then this is the IS number, okay? In EIGRP, this IS number has to be the same in the neighboring routes, okay? In all routers.
You have the one who chooses the number or it's a standard?
The number you can choose whatever you want, but it has to be the same in all the routers that you want to exchange routes using EIGRP. Because, for example, if you have a big topology with lots of routers and they can all form neighboring, whatever. If you put, for example, 110 here, 110 here, the IS number, 110 here, but here you place 20 and here you place 20, what's going to happen is that these are going to form neighborings. These are going to send routes between them. So this one is going to learn the routes that is here and here and here. But for example, this one will not learn the routes of this one, okay? Because this is in a different IS. And these will only learn the routes from each other, okay? So for example, in your project, if you are using EIGRP in all the devices that use layer 3, you have to put the same IS number in all of them, because if one of them you don't place, then the networks that this one know won't be shared with the other ones. Okay, so this is the first part, router EIGRP, and then you give an IS number. It can be whatever you want. This has the maximum value of 65,000 and something. Okay, there are IS numbers that are public and registered in the internet, but usually this isn't a problem in EIGRP because EIGRP does not communicate outside of the autonomous system, so you can put whatever number you want there. Okay? In BGP, for example, it's not like this. BGP also has an IS number, but in BGP, since it's a protocol that will speak between different autonomous systems, I cannot use an AS number that is already used by another autonomous system, and the AS numbers are regulated by IANA, has the IP addresses. Okay, and there is a public space and a private space also. Second, so this is just, I'm going to use EIGRP. Now I have to tell the router which interfaces are going to participate. Okay, so I want this one to participate because I want to do a neighboring here, and I want to announce this route, this network, and I want this one to participate. In this case, not to form a neighbor because there's nobody here. This is just a VLAN that is connected here with hosts, but I want to announce this network here. This is a /24. Okay, so how do I do this? I use the network command. This is what you sometimes mix up, because this is called network, but this is not to say that I want to announce a network, okay? For example, this command here is not telling the router to announce the 122.168.1.0 network, okay? And since I did not place the wildcard mask, this is like if it was a /24, okay? So this is not to tell, so you have to advertise this network. No, this is not how it works. That's why this mask is a wildcard mask. There's a space here missing. Okay, actually we can go here. It's the same thing and it's better. Okay, you see here, it has a space. So what this command, this is a wildcard mask, okay? So it's the opposite of a regular mask. A regular mask has the ones that pertain the network part, okay, and then the zeros are the host part. This is for matching, okay, that's why it's a wildcard mask. So this means what? The zeros here are what needs to be exactly the same. So for example, here I have 0.0.0, so that means that it has to be 162.16.1, okay? This has to match entirely, okay? The last octet is a don't care, 255. So this means what? This is a rule. What the router is going to do is, he's going to see, okay, he's going to go through all of the interfaces that it has. It's going to look at the IP address, and it's going to see if the IP address of each interfaces matches this rule or not. Okay, for example, this one here won't match because it starts with 172.16.5 and not 172.16.1, and I have 3 zeros here. So it has to start with 172.16.1, okay? So this one won't participate because it does not match that rule, okay? This one here, it starts with 172.16.1, so this one will match. So this one will participate. So he will do two things, okay? So fast Ethernet 01 has this address. I'm going to put it here with a mask. /24, okay? So what the router does is, okay, let me see if this matches with any network command that I have, if it matches with the rule. It matches. I have a command that is 172.16.1.0.0.0. So this starts with 172.16.1. So it matches this. So I'm going to try and form a neighboring relationship through this interface. In this case, I'm going to send a hello. Nobody's going to answer because there's no router here. Second thing it's going to do is it's going to announce the route of the interface. So it's going to announce the 172.16.1.0/24, okay, with cost 0. So sometimes you mix this up because if you look here, oh, okay, he's going to announce the /24 because this is a 24 mask reversed. But I could use a different wildcard mask here and this would work in the same way. Instead of this one, I could do network 172.16. Now actually in this case I can't because I have this .5 here. But this is a .5, so I could use, this is going to make me do some calculations here that I won't be able to do quickly. This could be a /22, which is, I think it's this 00.3.255, okay? So I could use this wildcard mask. This has a 3 here, okay? So if I'm not mistaken here doing this by heart, this means that this is for whatever interface that starts with 172.16.1, 172.16.2, 172.16.3, okay? 172.16.4, 16.4 does not match with this, okay? Because these 3 bits are not, only the last 3 bits are don't care, so actually I think this is 2, not 3. Okay, because I need to take 2 bits here for this to go 4 by 4. Okay, so this is a 000.2 here. Okay, so this means that the 2 last bits are don't care, but the other 6 have to match.
The last bits will be 2 plus 1.
Yes, it makes 3. 4 actually, because it's 1 1 is 4 in binary. Actually, no, it's just 4, it's 3. So this.
So bits all ones.
So everything has to be the same except for the 2 last bits, which means that this, in this case, it goes to 0 through 4. Okay.
Yeah, so 2 bits is.
Because 0, 1, and 2, these 2 bits don't change. But in 4, I already need this bit to change. Okay, because this one is 1 and this one is 2. So this 1, 1 is 3, okay? And to write 4, I will need this bit here. And this bit cannot change. Okay? So this, with this wildcard mask, only these 3 beginnings are valid. Okay? Okay? But this is just to show something. Usually you don't need to do a wildcard mask, a very complicated wildcard mask, because it's you only need to assure that nothing that should not belong to EIGRP will match that. Okay? I'm just doing this more complicated one for what? Because in this case you might be tempted to think that this command is telling the router to announce 172, 116.0. Actually this has to be .0 in this case. This has to be .0 in this case. Okay? Because only if it's .0 here, it means that it is from 172.16.0 to 16.1, 16.2 and 16.3. These are the only ones that match this. Okay? But sometimes you mix this and you look at this and say, okay, this is a network, this is the reverse of a /22, okay? This is the reverse of a /22. And sometimes I ask this on tests, for example, or on exams. And I put this command and tell you what are the networks that are going to be announced. And you have to go and see in this what are the networks that are on the interfaces that match. Those are the networks that are going to be announced. And sometimes you only look at the command and immediately say, oh, it's going to announce 172.16.0.0/22 because this is a reverse mask of /22. But no, that's incorrect, okay? This mask here is not to tell the mask that's going to be advertised. This mask is to give a rule to match the interface IPs, okay? This is why it is a wildcard mask and not a regular mask, okay? So that people don't mix both things. So in this case, this would be exactly the same. This one would match, this one would not. But the network that is announced is exactly the same. It's the network of the interface which is the same. It's the network that is on the interface, okay? So be aware of this. What this tells is not what networks are announced. What this tells is only which interfaces belong or not. The networks that are announced are then the networks that are configured on the interfaces. Okay? How does he know the network? Because the interface has an IP address, which is a host address, but it has a mask. And the router can tell by the mask which network is that. Okay, so this is going to be announced, the /24, which is the network of this interface, and this network here also, because I have here, this is a good example, because when I do not place the mask, this is the same thing that placing this. Why? Because this is class C. Nowadays there's no more classes, but we still sometimes use them. For example, Cisco still uses them for these things, to facilitate some things. Usually IP addresses were divided in 3 classes, A, B and C. Okay, class A is 10.0.0 something. Okay, class B is 172/16 something, and C is from 192.168.0 onward. Okay, so a router, when it sees something starting with 192.168.1, if I don't place anything here, he will assume that what I want to do is a reverse mask of /24. So it's like the same thing. This is exactly the same thing of writing here this 0.0.0.255. Okay, this is exactly the same thing. So in this case, I will ask again, what is the network that is announced? Okay, and although what's here is matching is a /24 wildcard mask, what's going to be announced is a /27, because that's what's in the interface. Okay, so what's announced is what's in the interface. It has nothing to do with this mask. Okay, this mask is only a rule to see if an interface participates or not. The networks that are announced are the networks of the interfaces. In this case, there's only one interface that matches this rule, which is this one. What's the network of this interface? It's 192.168.1.101/27, so that's the network that I'm going to announce. Okay. Okay, so configuration is just this: router EIGRP 1 IS number, then the network commands to just include what I want. Okay. Here you have another example. Actually, it's the same thing. Okay, this is what we saw earlier, and then the configuration of the interfaces. Okay, the networks are defined by this, not by this. Okay, this defines if these interfaces belong or not. The networks that are announced are defined by what I have configured here, which are the networks of the interfaces. Okay. In R2, same IS number, otherwise there's no neighboring, and then I have to include this interface, otherwise there's no neighboring, because if I don't include this interface, they won't form an adjacency. Okay, so I have to include this, so I have to create here a network rule that matches that IP, this one for example. Once again, this is the same thing that having this. Okay, so everything that starts with 192.168.1, that's the case, it will participate. Same thing, I need to create a rule. In this case, I created a rule to match anything that starts by 172.17.2, which is the case of the interface that I want to include. Now, this interface and this interface do not have routers. Okay? But I need to include them on EIGRP because I need to announce these networks. But the side effect is that these routers are going to try to send hellos here, okay? And it's useless. So I can do something, which is, I'm going to go back here, which is say that these interfaces are passive, okay? This is needed why? Because I need them to match the network command, because I need to announce the networks. But I don't want them to try to form neighborings, because there's nobody there to listen. Okay? So there's two ways of doing this. If most of the interfaces are active, then I use this command, which is and I tell which ones are passive. Okay? In this case, there is one active, one passive, so it's the same thing. But for example, you might have a router here that has a lot of networks. For example, this router can have 5 VLANs here. Each one is a network. Okay? Okay? There's layer 2 topologies here, and I have 5 VLANs, 5 different networks, and I only have 2 neighbors. But I want to include all the interfaces, because I want to do neighborings here and announce the routes of the links. But of course, I want to announce the routes of the VLAN. Okay, the VLANs. So in this case, I would have 5 passive interfaces and only 2 active. In that case, I can use another command. I don't know if I have it here. No, I don't have it here. So I can do another command, which is passive interface default, and this means that all by default are passives. And then I have to do the command in the reverse way. I have to do no passive interface to the ones. In this case, I would have to do no passive interface for these 2. Okay? So you can do both ways. You can, if you leave it, what's by default is that all are active. Okay? And then you use the command to tell which ones are not. But you can change the default to passive and then use the no passive interface to tell which ones are active. Okay? So this is the configuration. Very easy. Usually 2 or 3 commands. Router IGRP, IS number, then the network commands to include whatever I want. For example, in your project, it's just one network command, because you want to include everything that starts by 10.8. Basically, you want all networks to be announced. And then make some of the interfaces passive. For example, the SVIs can be passive, for example, because otherwise you will try to do an adjacency through the trunks. And he will do it, but usually it's not very good. And you don't even need it, because the trunks are already directly connected. So he won't learn any new routes through here. Okay? And then you can verify how show IP or show IP EIGRP neighbor. Then you will see if the neighborings are up, to see if you successfully formed an agency. Okay, then you can do the show IP route. Okay, there, show IP route EIGRP. This can show you the routes that are being learned via EIGRP. They have this code, the D. For example, in the project with the SVIs, you only have directly connected networks. When you start having EIGRP, and these ones are marked with a C from connected, and then you will start to have D routes that are learned via EIGRP. Okay. Then here you can show IP EIGRP interfaces. This will tell what if your network command is correct, then you will see the interfaces there that you wanted to include, and you can see if there is anyone that shouldn't be here. Okay, and then you can also do show IP IRGP topology. This will tell you the same information that the routing table will, but if there are alternatives, it will show the alternatives that you have. Okay, the passive we already saw, the passive interfaces. Then only 2 things are left to discuss. Okay, one of them we already touched, which was we might need to summarize announcements, summarize routes. Okay, we saw in the beginning that topology that have the 10 networks that we could in the core only know of 3 networks. Okay, the other one, which has the same goal, which is to have a smaller number of routes in the routing table, is a default route. A default route is also important because I'm never going to know all the routes. This is an interior gateway protocol. Okay, so an interior gateway protocol will learn the routes of that network. For example, here in the college, in the campus, the routers know the networks here, which are always the 10.1. something, which are the internal networks. But then when I need to go to the internet, I need to go to an IP that does not match any of the networks inside. Okay? So usually I need to have a default route. This is to go outside of my network. Okay? Then I can use BGP later. Instead of a default route, I can have BGP. For example, I can exchange BGP with my provider, my internet provider. But usually, even if I'm using BGP, I'm not learning the entire internet table because my router at home, for example, does not have the capability of that. It's millions of networks. Okay? So it will learn always a default network. A default network is this special network 0.0.0.0 with the mask 0.0.0.0. It means every network, and it means what? When this is in the routing table, what happens is if I do not find any match, it will always match this. Okay, this matches any network. So for example, you go to Google, you do a DNS query, you get an IP address which is a public IP. Okay, then you go to your gateway, and your gateway is exchanging EIGRP with the internal network. So it has routes to the networks that it knows inside, but it does not have a route for the public network of Google. If it has a default route, it will send to where the default route points. Okay? It's important that all routers have this route to go outside. Otherwise, you can go inside your network, but you can't leave your autonomous system. Okay? The other thing that might happen is that you might be learning via BGP the prefix of Google, but that's very unusual. Okay? Sometimes you can learn some prefix, usually the prefix that belong to your provider, but no more than that, because otherwise your router goes crazy. Okay? How is this done on EIGRP? Okay, you have this example here. This is a route that is being learned from an external IS. It could be something on the internet, for example. Okay, and this router is not even doing EIGRP here. Okay, router 3 is not a neighbor of router 2. Okay. But router 2, the only thing that router 2 knows is that this network exists because it's directly connected to it. Okay? So he knows that this network exists. Okay? So he knows that the network 172.31.1.0/24 exists and is directly connected to it. Okay? And I'm configuring this, and I know that this is the exit point. Okay, this goes outside. So what I'm going to do is I'm going to create a route using the command IP route, a static route, because I have no other choice. It's only this path, telling that to reach whatever network I don't know, the next hop is 172.31.1.2. Okay, which is what? My interface on this directly connected network. Okay, my interface is the next hop to where I send this. Then but now I want everybody to have this route so that they know then whenever they receive a packet to which they don't have a route, they need to send this to me. Okay? So I need to propagate this route to R1, for example. I need to announce to R1 that I can reach 0.0.0.0.0.0.0 with cost 0 because it's via a link directly connected to me. I need to tell this to him. The way to do this is inside of the configuration of router EIGRP, do this command, redistribute static. What this does is, I will use EIGRP to announce my static routes, okay, in the distance vector. So this will learn this route, okay, and then if it were more, it will propagate to the others, and this will also learn. They will add this cost, he will add this cost, imagine that is 100, and then he will say to the other ones that you can reach 0.0.0.0.0 via R1 with 100 cost, and so on. Okay? End to end, we have the summaries we already talked about. Okay, we're just going to see how it's configured. Okay? The advantage we already saw. So I can have whole areas that are, instead of having one entry for each network that exists in that area, if I only have one point of entry, there's no point, okay? For example, here, if I have 10 networks here, there's no point on these routers knowing about these individual 10 networks because the path is always through here. So they only need to know a bigger subnet that includes all of them. So whenever a packet appears that's for here, it will also match the bigger network. So it will go through here. Okay? Also, besides having smaller number of entries, it's also better because when there's failures that affect only one network, there isn't an update here. There's only an update if I don't have any of the networks, you see? If I can't reach any of the entire subnet is when I send an update. If I lose some of the networks, I don't update anything. Okay? There's some things we need to be careful here, which is, we need to be careful. For example, imagine that you have the same thing on this side with 3 routers. Of course, these networks have to be chosen in a way that the subnet that I use here is not the same one that I use here. Okay? And that this summary that I use here does not include any networks that exist here. Otherwise, these routers in the middle will be confused because they will receive 2 different routes for the same prefix. They won't be confused because that can happen in an algorithm. I can have 2 different paths. He's going to choose the smallest one, the shortest one, and that might not be the right one. Okay? So, actually in EIGRP, we have to be very careful to do this command, which is the no auto summary. Because by default, EIGRP will summarize. And it will summarize roughly, okay? It will do this by the big masks, meaning /24, /16, /8. So if you don't do the no auto summary, you can have things like this. For example, here you have 172 16.1.0/24, and here you have the .2. Okay, if you don't do the no auto summary command, EIGRP automatically will do this. He will announce 172.16/16, okay, and RT will do the same. It will send 162.16.0.0/16, okay? Because this is a class B. If it was a 10, an address starting by 10, it would be even worse. They would announce the 10/8, 10.0.0.0/8. Okay, and this you can see easily that this is a problem, okay, because in this routing table I have the network via R1 and via R2. So if, for example, the cost here is better, what would happen is that when I send things to, for example, this address, it will go this way because this cost is better, and the only thing that he knows is the big network. Okay, so this matches this and this, so he will choose the one with the least cost. If that's this, it will send here, and it's the wrong way. Okay, or if they both have the same cost, it will use load balancing, so sometimes it will send one side and sometimes on the other, and it will be bad. Okay, so no auto summary, and we just have to see which is the command to do the summary address. This is done in the serial interface, so the place where you want to do the summarization, so meaning that from that router onwards you only want to announce the summary. For example, if I want to do the summary here, then is in this interface that I do the command. Okay, here it would be on this interface. Okay, imagine that it is the gigabit 01, it would be in the gigabit 01. Okay, so I go to the interface through which I want to send the summary, and I do this command: EP summary address EIGRP 110, that he knows that is a summary through EIGRP, and then I do the summary. Okay, this is the network that I want to announce. In this case, I want to announce the 172.16.0.0/16. Then I use that mask. Okay, this will include all things started by 172.16, and I have to do the no auto summary. Okay. When I do something like this on R3, a special route is built. Okay, we just finished this, which is what you see here: a special network 172.16.0/16 is a summary, and the next hop is null 0. Why? Because I'm announcing a big prefix here, the summary. Okay, but people are going to send packets to the real networks, okay, or not. Imagine they can send me a packet for 172.16.4 that doesn't exist, for example, with this destination address. What will happen is I will receive the packet, and this one will not match with this one nor this one, which are the more specific ones. You see, does not match this one, does not match this one. It will match this one. And what will I do with the packet? I will discard it. Why? If I did not do this, then probably, if this doesn't exist, I will probably, in this case I don't have, but I might have the 0.0.0, a default gateway. So if it does not match this and it does not match this, it will match this. And most probably, this happens almost all the time, the summarizations are done in big parts where I'm sending things out. And most of the time the default routes are pointing in that same spots. So what happens is, if I don't have this, if I receive something which is not for me, because I don't have that specific network, but it matches my summary, it can be sent to me, and then I will send it back via the default gateway, and the packet will be here all life, all day, until the TTL expires. Okay? So automatically routers do this. Okay? So that if I receive something that matches the summary, but I don't have, I do not take the risk of sending it back via, for example, a default route. Okay? I have a route, it will match this route and it will be discarded. Okay? This on EIGRP, he does it automatically. on OSPF and ISIS, it also does it automatically, but for example, there are ways to do a summary route on BGP where this is not done automatically. And in that case, we have to do it ourselves. Okay? So, actually, we have here more slides. We already discussed this, but then in the next class I can just go over it again. But we already talked about this, which is the feasible successors and the rules and the maximum paths command that I was talking about.
Próxima aula vai ser só de exercícios ou vai ser uma aula?
Não